We begin with a staggering thesis, an idea born not in a telescope, but in the abstract realm of pure information. Dr. Kenji Tanaka, voiceover. For centuries, we've sought a fundamental ordering principle, from the music of the spheres to the standard model of cosmology. It's our best description of the universe, but it's incomplete. There are cracks in the edifice. Cracks that appear as subtle anomalies, unexpected cold spots in the faint afterglow of the Big Bang, galaxies clustering in ways that defy our neatest equations. This is where consensus ends, and a new investigation begins. Dr. Eris Thorne, interview. The standard model assumes space-time is a smooth, continuous fabric. But what if it's not? What if, at the most fundamental level, reality is discrete? A crystal, a universal lattice. Dr. Eris Thorne proposes that the universe isn't a canvas, but a tapestry, woven from finite threads of information. An infinite random sequence that by its very nature contains every finite possibility. Every book, every life, every history. Dr. Eris Thorne, journal voiceover. Log entry. The data resists. It suggests a structure we weren't looking for. Not a flaw in the signal, but a feature. A pattern hidden in the noise. It feels like staring at static, knowing the message is encoded within. To see this message, Thorne suggests we must stop looking across the static. We must change our perspective. By folding this ocean of raw data into higher dimensions, a hidden structure might emerge. Dr. Eris Thorne, interview. Think of it like a 2D drawing of a complex object. You only see a flat projection. But if you can fold it into the third dimension, you perceive the true object. We believe the cosmic anomalies are projections from a higher dimensional, crystalline structure. This journey, then, is not about creation. It is about perception. A quest to find profound order and perhaps reality itself within the static of unbound chaos. Dr. Kenji Tanaka, voiceover. We are witnessing a potential paradigm shift. It's a debate between the universe as a perfect fluid versus a perfect crystal. The evidence will decide, but the question itself changes how we see everything. The first fold awaits. A new way of seeing what has always been there, waiting to be discovered.
The radical idea of a universal lattice, that space-time itself is not a smooth fabric, but a grid of discrete points, is not a flash of modern insight. It is an idea reborn, with an intellectual lineage stretching back a century. Professor Kenji Tanaka, on-camera interview. To understand this theory, you must understand a fundamental debate in science, the continuous versus the discrete. Is reality a smooth, unbroken line, or is it made of fundamental, indivisible pixels? This question echoes from the Greek atomists to today. The journey begins not in physics, but in pure mathematics, with the thought experiments of French mathematician Émile Borel, and it finds its language in the information theory of Claude Shannon, who taught us to see the world in terms of bits and data. Dr. Eris Thorne, on-camera interview. The theoretical bedrock is a concept called a normal number. Imagine an infinite, non-repeating sequence of digits. A normal number is guaranteed to contain every finite pattern of digits somewhere within it. Your birth date, the text of a novel, the code for a simulated universe. Mathematically, it's all in there. A single, all-encompassing sequence, a cosmic code. This mathematical certainty breathed new life into ancient philosophical debates. For centuries, thinkers grappled with the implications of a universe where all possibilities might be pre-written into its fundamental structure. Professor Kenji Tanaka. Determinism versus randomness. Free will versus a preordained path. These aren't just questions for philosophers anymore. If the universe is informational, These questions become central to physics. This historical foundation provides a new lens through which to view the persistent, unsettling anomalies in our most advanced observations. Tiny deviations in particle accelerator data, subtle alignments in the cosmic microwave background. These are the cracks in the smooth facade of continuous spacetime. Dr. Lena Petrova, on-camera interview. The success of general relativity is undeniable. For over 100 years, the model of a smooth, continuous spacetime has worked. Any new theory, no matter how elegant, must first explain everything that Einstein's theory does. And then it must explain the anomalies. That is the bar. Dr. Eris Thorne, voiceover, as if reading from a journal. The anomalies aren't errors. They are signals, whispers from a deeper level of reality. The universe isn't failing our equations. Our equations are failing to describe its true, discrete nature. Thorne's universal lattice hypothesis proposes that this deeper level is computational, a network of pure information from which the illusion of space, time, and matter emerges, just as patterns emerge from the chaos of a normal number. Dr. Thorne, we are now building simulations to test this. We model a discrete spacetime and see if it evolves into a universe that looks like ours. If we can replicate the large-scale structure of the cosmos from a simple set of informational rules, that will be powerful evidence. From an abstract mathematical proof to a testable cosmological model, the stage is set. An ancient idea, armed with modern computation, is challenging the very fabric of reality.
For a century, physics rested on the assumption of a smooth, continuous reality. But a series of jarring anomalies in our most sensitive instruments hinted at something else entirely. Dr. Alastair Finch, voiceover, journal. The data from CERN, the subtle anisotropies in the cosmic background, they don't whisper, they scream. A graininess, a fundamental resolution limit to reality itself. The theoretical gives way to the transformative. Our investigation pivots on a single, powerful catalyst, the first dimensional fold. We take the infinite one-dimensional line of binary text and wrap it upon itself, again and again, until it forms an endless two-dimensional plane. Dr. Lena Hansen. It's a fascinating mathematical construct, but the information content is identical. A zero is still a zero. The arrangement changes, but it doesn't create substance. Dr. Alastair Finch. That's where the consensus view falls short. The arrangement is the substance. The underlying information remains unchanged, but its new arrangement gives rise to an entirely new emergent property, imagery. Suddenly, the abstract library of every text becomes a universal gallery of every possible image. Dr. Kenji Tanaka. This is a monumental shift in ontology. If the lattice contains every possible image, it's not merely a model of reality. In a very real sense, it is a higher dimension of reality. We visualize how this lattice, through sheer probabilistic necessity, must contain a perfect photograph of every face, every star, and even the viewer themselves, captured in this exact moment. The implications are staggering. Dr. Lena Hansen. It remains a philosophical curiosity. Where is the falsifiable test? How does this lattice interact with the known forces? Without that, it's not physics. Dr. Alastair Finch. The graininess is the evidence. The slight variations in the speed of high-energy gamma rays, the subtle repeating patterns in the cosmic microwave background. These are the seams Dr. Hansen believes don't exist. This milestone transforms a mathematical curiosity into a profound visual paradox. Dr. Kenji Tanaka. We are at a precipice. Is the universe a continuous story being written, or is it a finite library where we are simply turning to the page we happen to occupy? The debate pushes the very boundaries of what we mean by real, leaving us with the most profound question of all. Are we the authors, or merely the text? Now, we dive deep into the staggering implications of dimensional folding, reconstructing what it means to find not just text, but coherent visual narratives encoded in the universe's foundational structure.
We're forced to move from the static 2D plane to a 2D plus time structure by introducing a third axis of sequence. It's a profound shift in perspective. Each slice of this new dimension is an image, a single frozen state of reality. And a succession of these correlated slices creates motion, a video, the universe as a cosmic film. Computationally, it's an immense data structure. Our algorithms search for the correlation engine, the projector's hum, that connects one universal state to the next. The analysis then becomes deeply personal, exploring the certainty that a complete, frame-by-frame cinematic recording of your entire life, from birth to this very instant, exists as a continuous path through this informational space. This echoes ancient philosophical ideas of a cosmic record, but grounds it in mathematics. The impulse to see life as a recorded narrative is timeless. Early information theorists wrestled with this. An unearthed journal from a mid-century pioneer reads, "If information is physical, is not physicality then informational? The reel of film contains the story before it is projected. Does space-time not contain hours? We must then examine how the sensation of time itself may simply be an emergent property. Time could be a side effect of informational coherence between adjacent frames in the lattice. We experience time because our consciousness processes one frame after another in a causally consistent sequence. A universe not of matter and energy, but of information and geometry. A story already written. And we are simply living out our chapter, frame by painstaking frame."
The universal lattice theory, elegant in its two-dimensional form, encounters its first great obstacle when projected into the universe we know. As we fold the lattice into three spatial dimensions, the grid begins to bend and connect, forming a complex 3D structure. Coherent worlds emerge, but they are imperfect. We call them mirages. They are fundamentally discrete, composed of three-dimensional pixels, or voxels. It's a cosmic architecture, a blueprint. This revelation depicts a universe built not from smooth curves, but from finite blocks, a reality resembling a vast computational game of Minecraft. This raises a critical, perhaps existential debate. Is this block-like structure an insurmountable limitation? A sign that the lattice can only ever be a crude approximation of reality?
Dr. Petrova, the mathematics are compelling, but science demands observation. The lattice predicts a quantized space at the smallest scales. Yet general relativity, tested for over a century, is built on a smooth, continuous spacetime. The established model works flawlessly.
The tension between these two views is not new. It echoes the quiet frustrations of pioneers from a century ago. We see a grainy black and white photograph of Professor Alistair Finch at a chalkboard covered in equations. Professor Finch, archival. "From my journal, 1954. I have wrestled with the continuum. Its infinities are a mathematical convenience, but are they physical? What if the fabric of space is not a fabric at all, but a tapestry, woven from finite threads?" Finch's ideas were largely ignored, but they planted a seed. Today, Dr. Thorne argues this tapestry is the key. The anomalies we see in particle accelerators, the subtle temperature variations in the cosmic microwave background, they don't fit perfectly with a continuous model. They are the faint echoes of the lattice, the seams in the tapestry. This brings the debate into sharp focus. One side sees the lattice as a radical but necessary new framework, capable of explaining data the standard model cannot. An alternative interpretation is that we simply have gaps in our current understanding. Proposing a pixelated reality because of a few anomalous data points is a monumental leap. It feels computationally simplistic. Two opposing visions of our universe emerge. Is it a grand analog masterpiece, smooth and indivisible? Or is it the most sophisticated digital simulation imaginable,
running on an operating system of ones and zeros. The limitation is the theory's greatest strength. It suggests the universe is fundamentally computational, that physical laws are the output of an algorithm running on this lattice. The path forward lies in observation, pushing our instruments to the very edge of perception, searching for the ultimate pixel at the bottom of reality. The answer is waiting at the resolution limit of the cosmos itself.
Narrator. Our inquiry reaches peak forensic depth as we analyze the chasm between the block world mirages and the observed physics of our universe. The lattice hypothesis, in its simplest form, presents a beautiful, ordered grid. But reality is not so clean. Particles are not cubes. Forces are not rigid, grid-based interactions. We deconstruct the evidence, and the simple model shatters against the known universe. Dr. Anya Sharma. The beauty of the Standard Model and general relativity lies in their continuous symmetries. These mathematical languages describe a world of smooth, flowing fields. Any proposed fundamental structure must somehow give rise to this seamlessness. A simple cubic lattice just doesn't have the vocabulary. This critical disconnect is where the search truly begins. The evidence from quantum mechanics and general relativity highlights the subtle, unbroken symmetries that define existence. It's a modern echo of an older puzzle. Historical monologue, voice of Dr. Alistair Finch, journal entry. Nature does not appear to compute its next step. It flows. If there is a gearwork beneath, its teeth must be infinitely fine. The analysis now focuses on this critical turning point, the failure of the simple 3D plus time lattice to reproduce the fundamental rules of existence. It cannot bend space as gravity dictates, nor can it host the delicate dance of quantum fields. The entire premise seems flawed. Or is our method of folding the universe too simplistic? The question sharpens our focus. Dr. Ben Carter. We're combing through terabytes of cosmological data, not for pixels in space, but for statistical artifacts, shadows that a more complex geometry might cast on the early universe. It's a search for a pattern hidden within the noise. With the old model discarded, the search intensifies. The goal, a more sophisticated geometry, a structure capable of encoding the seamless, non-pixelated fabric of space-time and matter as we experience it. A new architecture for everything.
The central paradox of modern physics was absolute. A universe that appears smooth and continuous, yet at its smallest scales, is governed by the discrete, pixelated jumps of the quantum world. For decades, it seemed an impassable divide, the blocky mirage of reality. Professor Jian Li. Science history is a graveyard of beautiful ideas slain by ugly facts. But it's also a story of seeking synthesis. From Newton's universal gravity to Einstein's spacetime, the drive is to find the single elegant principle beneath the chaos. The search for that principle led not to the cosmos, but to a place far more abstract. A breakthrough emerged from the archives of mathematics, revealing a hidden pathway to continuity. Dr. Eris Thorne. The error wasn't in our physics, but our geometric imagination. We were trying to build a continuum out of simple blocks. But what if the blocks were shadows? The secret lies not in adding more simple dimensions, but in the projection of higher dimensional lattices into our familiar space. Dr. Eris Thorne. Imagine a 6-dimensional crystal, a perfect repeating lattice. We can't see it directly, but its projection, its shadow cast into our 3 dimensions, can be something else entirely. We uncover the groundbreaking discovery that complex geometries can generate quasi-crystalline patterns, a structure that never perfectly repeats, avoiding the rigid grid of a block universe. Dr. Eris Thorne. It generates the illusion of perfect smoothness from a discrete source. It's the ghost in the machine. This pivotal synthesis provides the missing link, a plausible mechanism for an underlying informational structure to produce a reality that behaves as if it were perfectly smooth. Dr. Lena Petrova.
It's mathematically sublime, a beautiful model. But for an experimentalist, beauty isn't proof. The challenge now shifts from the chalkboard to the laboratory. Dr. Lena Petrova, if this shadow exists, it must interact with our world. It must leave a signature, however faint, in the debris of high-energy collisions or imprinted on the cosmic background radiation. The blocky mirage gives way to a far more elegant and promising model, a universe woven not from points on a grid, but from the intricate, non-repeating shadows of a higher dimensional reality. The hunt for that shadow has begun.
With a plausible model for a continuous, information-based reality, we are forced to confront the global ramifications. The elegant, yet terrifying conclusion is that the distinction between a simulation and a so-called base reality simply dissolves. The moment this model holds, our foundational dichotomy of real versus simulated becomes meaningless. It's not a copy. It is just another instance, a self-contained pattern. The laws of physics are recontextualized. They are no longer fundamental, universal edicts, but rather emergent rules, local bylaws governing relationships within one specific coherent structure. Primary source, Journal of Dr. Alara Vance. The equations don't lie. The physical laws we cherish are not bedrock. They are emergent properties, bylaws for our specific corner of existence. This paradigm shift ripples through our most fundamental fields of knowledge. In cosmology, the Big Bang is no longer a singular event, but perhaps the boot sequence for our local system. In philosophy, the nature of being is questioned anew. In theology, the concept of a creator is radically transformed into that of a first principle or an initial state of order. It challenges our very understanding of creation, consciousness, and existence itself. We must analyze the profound impact, the realization that our entire cosmos, with all its history and all its life, could be just one of countless realizations floating in an infinite ocean of randomness. Each one a bubble of order in a sea of chaos. We are distinguished only by our internal consistency, our complexity, a single perfect crystal formed against an eternity of noise.
We arrive now at a profound synthesis. The journey through quantum mechanics and general relativity leads to a startling conclusion that the existence of a perfect informational analog to our universe, a universe born from pure data within an infinite lattice, is now considered a near certainty. The modern challenge, therefore, is not one of proof, but of detection. The debate has fundamentally shifted. Dr. Eris Thorne. Exactly. We've moved past asking if and are now consumed with how. It's no longer a philosophical exercise. It's the largest search problem in history. We've termed it cosmic archaeology. Cosmic archaeology. The painstaking process of sifting through a potentially infinite space of informational possibilities. To tackle this, scientists are developing entirely new branches of computational analysis and theoretical mathematics. Their goal is to find signatures of high-order coherence, what some are calling informational fossils. These are not fossils of bone, but of physical laws, of emerging complexity, even of consciousness itself. Dr. Kenji Tanaka. This search for fundamental patterns is a modern iteration of a quest as old as science itself. From Democritus's search for the atomon, the uncuttable piece of reality, to today's search for the fundamental bit of information. It's the same question, simply armed with vastly more powerful tools. The primary countermeasure against being lost in an infinite sea of digital noise is the search for patterns that are not just ordered, but are uniquely complex. Professor Lena Hallstrom. The signal-to-noise ratio is the great barrier. Randomness can produce fleeting moments of apparent order. That isn't enough. The real challenge is finding a pattern that is self-referentially aware, a structure that contains a description of itself. That is the potential hallmark of a realized, conscious universe. A self-referential pattern, a system capable of observing itself. This is the signature they seek, an echo of awareness resonating within the code of reality.
It suggests that consciousness isn't an accident of biology, but perhaps a fundamental property of a sufficiently complex system. The search continues, sifting through the cosmic static, for a sign that we are not just observers of the universe, but a reflection of its underlying computational soul. A universe waking up to itself.
Narrator. For a century, our understanding of the cosmos has rested on a foundation of elegant continuity. Space-time as a smooth, unbroken fabric. But at the fringes of our perception, in the noise of our most sensitive instruments, cracks have begun to appear. Subtle anomalies and patterns inconsistent with a perfectly smooth universe. Dr. Lena Halstead, historian of science. The established model is incredibly robust. General relativity, the standard model, they work. So when these tiny anomalies, these digital ghosts in the data, show up, the first instinct is always to attribute them to measurement error. Dr. Aris Thorne, lead physicist. Error is a possibility, but when the same error appears in data from particle accelerators and then echoes in the cosmic microwave background, it stops looking like noise. He's referring to a faint, almost imperceptible pattern, a stippling effect on the very canvas of reality, a structure where none should exist. Dr. Lena Halstead. It's a classic paradigm shift moment. We've seen it before, from Newton's mechanics to Einstein's relativity. When the old map no longer describes the territory, you need a new map. What if the anomalies aren't cracks in the fabric, but the fabric itself? The fundamental pixels of our universe. A compelling theoretical framework that could unify the disparate realms of quantum mechanics and general relativity. Dr. Aris Thorne. The universal lattice theory posits that at the smallest possible scale, the Planck length, space-time isn't continuous. It's a discrete network, a computational structure, a concept that reframes our entire conception of reality, not as matter and energy in empty space, but as pure information processing. In this retrospective, we see our universe not as a unique creation, but as an inevitable pattern of information, a coherent story told by randomness. Dr. Aris Thorne, monologue/VO. The long-term future of science may be defined by the quest to navigate this universal lattice, becoming explorers of a landscape of pure possibility. Yet, this horizon carries a profound final warning. If we were to find another reality mirage, or even our own, from the outside, would we be able to recognize it? Pause. The ultimate takeaway is a humbling reorientation of our place in existence. We may not be the authors of our story, but rather a perfect, inevitable sentence written in the infinite book of everything.